for this audience, I want to give the problem statement right away instead of give a whole bunch of motivation, 10 minutes, and then wait the problem statement to the end. Okay.
Lalitha, one more thing. We just had a coding theory class in which I taught locally recoverable codes from 9:30 to 11.
Oh, okay. So how many of you were there in the class?
Yeah.
Okay. Wow, that is even better. I didn't know that. Sorry.
Yeah.
Okay, all right. So yeah, consider a code C, continue code C, okay, with parameters NKD. So I just want to know, I hope all of you know this notation, right? NKD in code, in your codes, all of you know the notation. I will start from students.
Actually, I don't know.
Okay, yeah. So this is N is a block length. So assume this is over FQ. Okay. So FQ is a finite field of Q elements, and C is a subspace of FQ. FQ to the N. So N is called the block length of the code. K is called the dimension. Dimension because as a subspace that is the dimension in FQ to the N. And dmin is the minimum distance of the code, which is nothing but min over x not equal to y, having distance between any two vectors in the code. Okay, so x, y in the code. So that is the minimum distance of the code. So we call the parameters quickly, and then there is something called a singleton bound, which relates these parameters of the code. And this can be actually thought of as it's an alphabet independent bound. So I will say why it is alphabet independent. It says the min is less than or equal to n minus k plus 1. So that is the relation between the three parameters, and it's said to be alphabet independent because in this bound q is not coming into picture. Okay, and the class of codes which achieve this boundary equality with d1 equal to n minus k plus 1 are called MDS codes, which is maximum distance separable codes. Okay, and Reed-Solomon codes are examples of MDS codes. Examples of MDS codes, and there is also something known as MDS conjecture. So I'm just setting some background, that's all. So I'm not maybe precisely writing it, but the gist is something like if you want to have an MDS code, need a Q which is of the order of K, let's say, or N. So we cannot have a code with very low alphabet, I mean MDS code over very low alphabet. So that is not possible.
Omega.
Yeah. Right. So this is the MDS conjecture itself. Okay. So and Reed-Solomon codes kind of meet it. I mean, in the sense it's not exactly the numbers, but the field sizes required are of the order of n. So that is what are needed. I'll define Reed-Solomon codes in case at some time it is required. But as of now, we will just go into the locally recoverable codes themselves. Any questions, please feel free to stop me. Okay, because sometimes, just for the flow, I'm writing things pretty fast. Okay, but if you have questions, please feel free to stop me. Okay?
You can scroll the book.
Oh, yeah. Sorry. This, right? Oh, this way or this way?
The red one.
The red one. Okay. But I use the board so fast, I think I should have the time to scrolling. I don't know. Or maybe I should use better use of space. Let's see. So this second set of codes, which we are interested in, are known as locally repairable / recoverable codes. But for them, either this way or that way, the abbreviation still remains the same. They are called LRCs. This term itself is coined by a group from Microsoft Research. Parikshit Gopalan, and I know these two people very well, but there are others in the group also. In their paper, in one of the TIT's paper. So their setting is like this. So there is a code C, again with parameters n, k, d, n. So they introduce another parameter called R, which is known as a locality parameter. And what does this locality parameter state is that, so suppose if I have an arbitrary code word, I'm just looking at the vector, which is of length C1 up to Cn, right? So I look at any code symbol Ci, and I should be able to recover this by contacting at most R other nodes. So Ci, so let's say that set is some S, which is some indices I1, 2. For now, IR, but it could be smaller, that's okay. Right? And Ci itself is some function of C1, C2 up to, okay, Ci1, Ci2 up to Cir.
Yes, right. For every set, every I, there is a different yes.
Yes, correct. Yeah, so sorry for the notation. Yes, that's correct. Okay. So the way it is that to recover this one particular code symbol indexed by that I, we should be able to contact at most R other code symbols. Okay, contact in the sense of system terminology, that's what. But just mathematical terminology, so the Ci is a function of at most R other code symbols. Okay, and so then if this property is true, then Ci is said to have, or the ith coordinate, ith code symbol is said to have locality R. So that particular code symbol is said to have locality R.
So
and the code itself.
I is not an SI.
But I did not write I as part of SI already.
Okay.
Right? So it's different. Yeah. Okay. Okay. And the code itself is said to have locality R. So we have two terminologies. I think maybe it's good to just say both of them. So let's say this here. I will switch anything. So C is said to have locality / sometimes if both forms of locality are there, I'll call it in some way. So we call it information locality. If for some information set, again, so this is some other I, subset of N. Okay. Each Ci, each I in this I, such that Ci has locality R. Okay. So which means that there exists an information set in which each code symbol has locality R. That's all that I'm saying.
So what kind of function is it? Always a linear function or?
So we will, while constructing them, yes, we will construct linear functions. But in general, it could be non-linear also. Because all that we want is we want to determine Ci looking at all the other things. How they are helping is immaterial as such.
But for a linear code, if there is a function, there will be a linear function.
Correct. So and looking at linear code, so we will quickly move to parities only. I mean, so because if I have CI and all these CIs a parity which satisfies those, then we'll be able to compute CI as a function of the others. So that is right. So this is information locality, and there is another notion which actually we have introduced also called all symbol locality. It's said to have. I'm sorry, sometimes I write the whole sentences also, but that just gives me some time to think, write, and all that. Sorry about that. Okay, I do it in my class. All symbol locality. If this for each all I in n, for all I in n, the I has locality R.
So first definition of vector. So what is preventing I from being empty?
No, this has to be an information set.
Information
which
locality
means
with respect to a set.
No, information set.
information set for a code means that that
Oh,
has
I
to
see.
span all the.
Okay, so those coordinates determine all other coordinates.
Yes.
Oh, I see.
Yes.
Okay.
So for so this I has to be an information set. So it cannot be empty. It has to be of the size k.
Okay.
In particular, if it's a linear code, you can assume this is a systematic code and you're asking these message
Yes.
bits.
Yes.
Okay.
Correct? So in this setting, actually only information locality, using only this, there is a singleton like bound which can be proved, which is that b1 is less than or equal to n minus k plus 1 minus something. So this I call exactly singleton bound, and this I will call as penalty term because of locality. And this is k by r minus 1.
Sorry, can you tell me again what is information set?
Oh, the information set, suppose if you look at a linear code, right? So generator matrices of linear codes, right? So suppose if I look at generator matrix of any code, right? And if I look at G restricted to that set, it has to be of rank K. Okay. So not everything will be of rank K,
Okay.
right?
Yeah.
But that is an information set. Okay. So this I will not go into the proof of this, but it's a very nice proof which can be taught in the class. All that is happening is that it's like, so there is a yeah, I will not go into the proof of that. If I go into the proof of that, then it's like it will go in a different
So
direction.
is it achievable? So very first code.
Yes. It is completely achievable. So codes with information locality, okay, codes with info locality, achieving this bound are very easy. Achieving bound 1, so it's called 1, are very easy. They're called pyramid codes. Okay. And all that is done in a pyramid code, I can tell you what is done also in a pyramid code, is easy to see. So I take a generator matrix of a systematic MDS code. So I have I and P. Okay. Now what is done is that this I will just modify it to get the system generator matrix of this code. One thing, I will just say R divides K. If R doesn't divide K, it can be slightly modified. That's okay, right? So what is done is that here, for getting the GLRC, for example, right, the I remains as it is, and we take the first parity column in this. How many columns are there? There are, so this is K cross N, sorry, this is K cross K, and this is K cross N minus K, right? So we take just the first column in this, so the rest I will call it P dash, it stays as it is, right? Only the first column is picked, and then it is broken down and placed as diagonal things. How many of them is K by R of them? Okay. So earlier, whatever was one vector, which was P1, P2 up to Pk by R, right? So now we are just splitting it into things of size R and placing them in the diagonal. Okay, and this is exactly a pyramid code, and it achieves this bound with equality. Okay? If R doesn't divide K, also small tweaks of this will work. Only thing which I have not told you, again, this n, you should not actually start with n for the systematic code. If finally you want something of n here, okay, which means this is n, right? Here we are starting with a different MDS code. The dimension is still k, the length has to be adjusted appropriately. So that's all there is.
You start an MDS code with distance given by that,
Correct.
not n given. Distance
Correct.
given by that, and
Yes.
because this operation does not change the distance.
Yes. This operation does not change the distance. In fact, because you are only splitting the code words, so I mean, whatever code words are there, as it is, their weights can only increase but not decrease when you are splitting them.
So I just want to make sure I understand.
Yeah.
So the new generator matrix is going to involve I
Yeah.
plus K over R other columns
Plus
P
P
prime.
dash.
Okay,
Yes.
okay, fine.
That's exactly that other K over other.
Yes.
Right? So this is a simple code which achieves this bound, and the field size as such for this also is pretty easy. Means it's the same as MDS code, that conjecture only. Okay, so all these things were solved in the first paper itself. Then the paper which was done by, because again it's a slight detour, we are not going to maximally recoverable codes, but it's a nice fact to know. So I can tell you that. So the next follow-up paper.
You didn't scroll this.
No, I think okay. So that it's there, right? That's what you're saying. Yeah.
Yeah, in case you want to make use of
Yes,
any part.
Sure. Okay. So codes with all symbol locality are slightly trickier to construct. We don't get a simple construction like that. Means in the sense, yeah, and but they were done in a paper by Tamo and Bar, and this has won the TIT best paper award. That has won for some other award. This has won some other award. So it's like in LRC, these are the two landmark papers, I would say. Okay. This construction again, it is a neat thing of Reed Solomon codes. Okay. And maybe I can explain what is going on there also, just for so that I don't leave you in suspense. Okay. So, but in this paper, they have modified Reed Solomon codes in such a way that they can construct locally recoverable codes which achieve that bound always. Okay. And the field size is also quite minimal. So prior to Tamo and Berg, there were other groups from Israel and all that who have done this construction, all symbol locality for all parameters, but their field sizes were very high. Okay. And that means not so interesting, not so much interesting as this one, which had brought down field sizes to almost order of n again. Right? So what are these codes? Because it is quite nice to know, I will just state that codes. For that, I will require Reed Solomon codes also. So what are Reed Solomon codes? I have a message polynomial. Okay, so I have a message vector. Let's say I have m02 mk minus 1. This is taking on this fq to the k, right? And I form a message polynomial f of x. Sigma equals 0 to k minus 1 and I x to the I, right? So we evaluate this polynomial at n distinct points in the finite field, right? So pick alpha 1 to alpha n, right? And the code word itself will be corresponding to this message. The code word will be f of alpha 1, alpha 2, f of alpha n, right? And this is an MDS code, can be seen easily just because, so one way to think about it is it's a generator matrix. If you see, the generator matrix of this code is what is known as a Vadlamani matrix. So it will be like 1 alpha 1 alpha 1 square square up to alpha 1, 2, 1, 2, and so on and so on. And any k by k matrix in this, right, is full rank. And that already gives you the thing that the minimum distance actually is n minus k plus 1. Okay, I mean a few set of arguments that I'm missing, whether this is basic encoding theory, right? So this is an MDS code, okay, which means this achieves singleton bound with equality. Achieves so d-min equals n minus k plus 1. Okay. So what does Tamo bar codes do? Okay. So in this, what is done is, again, I have M0 to Mk minus 1. Right? So now, again, let's say R divides K. What I have is d1 is equal to n minus K plus 1 minus k by r minus 1, right? And the way I want to look at it is actually here I have I equal to 0 to, what is the correct number I'm thinking? So I think it has to be n minus. Is it this minus 1 which is even cancelled or plus minus 2? Yeah. So this one is some number k plus k by r. I forget if it is minus 1 or minus 2. I think it's easy to calculate, not a big deal. Okay. So, but the way it is done is that okay, I can tell you, and then we can perhaps write a closed form expression. What is done is, see, the minimum distance already suggests that your maximum degree of the polynomial actually has to go up. Okay, and the way the maximum, so their first trick, how they came up with this construction, which I think Barg told to Professor Vijay Kumar and they told to us, let's say, is that here you have consecutive powers of from 0 to k minus 1, right? Here you want to still have k coefficients for the message polynomial, okay? But the d-min somehow suggests that it should not be consecutive powers, okay? So what you do is that we take r powers and skip 1 power, okay? And keep doing it till all the k are populated, okay? So as it is, I'm not, just comfortable writing the expression directly. Perhaps I don't, but that is the case. What is happening? Okay. So you are taking r powers. I mean, in the sense, r coefficients. So I have m0 up to mr minus 1. So that actually, I think I could, write it not like a closed form, but slightly better. So it is m0 plus m1 x plus dot 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 m r minus 1 x to the r minus 1. Okay, so this is r terms in this. Skip 1 power, okay, which means x to the r is skipped. Then the next one, which is mr, will go to x to the r plus 1. Okay, so which is mr x to the r plus 1 plus mr plus 1 x to the r plus 2 and so on. And we keep doing this until all the k coefficients are complete. Okay, so the two things it has to satisfy. So this is how the message polynomial itself is formed. The message polynomial is formed this way. Then evaluation set also, because in the case of Reed-Solomon codes, the way we were doing this, we were picking evaluation points as any n distinct elements in the finite field. So that will do, right? Here in this case, any n distinct elements again will not do. You have to pick the evaluation points also carefully. How to pick them is that is as follows. Okay, so I will have sets like A1 to A n by r plus 1. Okay. So here what we are thinking is those repair sets, whatever we have said here, right? SI, etc. Okay. So in this construction, the way these are organized is that as if they are disjoint repair groups. Okay. So what is meant by disjoint repair groups? I'll tell slightly more. Let us see. Scrolling perhaps. So I have this C, which is C1 to Cn, right? Okay. So I'll assume that my repair groups are in this way. Disjoint repair groups means I have C1 to Cr plus 1, Cr plus 2 to. So this is part of the code construction. I mean, it's not that the locality is giving you. Code can also be constructed this way. Okay, so the LRCs can also be constructed with this structure. And it is somewhat easier to imagine. So that is the reason, and you don't lose anything by having disjoint repair groups. So that is the reason this is used. Okay. What is meant by disjoint repair groups? I will partition this N into groups of size R plus 1. Okay. So this is 2R plus 2. Okay, sorry. Yeah. So this is another repair group and so on. Okay, up to Cn. So this is a repair group, means that if any one node fails in this, or any one node is lost, the other R are helping it. Okay, and it is easy to see this in terms of parity check matrix, for example. If such disjoint repair groups are there and it's a linear code, what it means is that there is a parity involving this R plus 1 coordinates, right? And there is a parity involving the next R plus 1 coordinates and so on. So there are n by R plus 1 parities, and the repair groups are disjoint because the way it is constructed is C1 is getting repaired by C2 to CR plus 1, but C2 itself will be repaired by C1 and other than C2 the other things in that repair group. Correct? So that, and also linear codes very easily give that property. Whenever you have a parity with all the coefficients which are non-zero, then any one can be repaired by rest of the others. So that also is true.
So why don't we construct this locally recoverable codes using this parity check matrix? I mean, just take H where you have consecutive odd elements.
You don't have distance.
You don't have distance provided, right?
So the general thing about parity check matrix is that, so we could do this. Okay, so I have parities of this. I'm just showing the supports like this. Okay, so the number of parities you will have is n by r plus 1. Correct? But what should be the, and all these are linearly independent, so that is also clear, right? So, but what is the size of the parity check matrix itself is n minus k, right? So, in addition to what these are called, so these are called local parities. Okay. To construct LRCs, we should add what are called global parities also. Okay, means some more rows. Okay, and it is, I think, necessary that they should have non-zeros everywhere. So that also perhaps can be proved. But they are called global parities. Some more rows have to be added. How many have to be added? It has to be n minus k minus n by r plus 1. But then any set of rows will not work because all that we need, I mean, if you want to be optimal with respect to the minimum distance, right? So it comes from the parity check matrix also. One property of the parity check matrix is that any, d-min minus 1 columns of the parity check matrix are, have to have, I think, what is the rank of this? I have to be linearly independent. Okay. So this is a basic property of a codes with, a parity check matrix with codes nk d-min. Okay. So, but all that we are asking is when we are adding rows, this has to be satisfied for the d-min given by that bound. Okay. If that is satisfied, of course it will be. So otherwise, that is where is a construction problem coming in. Right? Okay. So, why did I get here? Is because, so now I want to tell you, we are going to construct code with disjoint repair groups, right? But using polynomials, okay? So, but then when I have disjoint repair groups using polynomials, it just means I have to tell you in each repair group what are the evaluation points and do they satisfy any condition or not. Okay? So let A1 be the points corresponding to first repair group. That's what I'm saying. So when I said A1, A2 up to AN by R plus 1, so this is like the set of points are alpha 1 up to alpha R plus 1. Okay? A2 is alpha R plus 2 up to alpha 2R plus 2 and so on. Okay? These are the evaluation points and they kind of correspond to the code locations, I mean the coordinates in the code anyway, right? So what is the additional condition? One is in the message polynomial we are skipping powers. The second is that f of, alpha 1 should be equal to f of alpha 2 should be equal to, okay, am I saying it right? No, not f. Alpha 1 power r should be equal to alpha 2 power r equal to alpha r plus 1 power r. So which means that there is this one particular polynomial x to the r which is taking constant value within that repair group. Okay. This has to be true within that repair group. And similarly, the same polynomial should be constant on the other repair group also, but their values themselves can be different. Okay. So these have to be equal. The next set of equality is alpha to r plus 2 should be equal to the power r should be equal to alpha r plus 3 to the power r and so on. For the next repair group also, x to the r has to be constant. Okay. So you
mean alpha 1 to the power r plus 1, no? The exponent is r plus 1.
No, it is r.
It can't be the case, no?
Then we can't have R plus
We
one.
can't have R plus
that
1
has the
distinct.
same.
We can't have r plus one distinct guys which are all roots of a degree r polynomial. What you actually need is r plus 1 because every r plus first coefficient is 0. Therefore, the exponent is r plus 1.
I don't think so. See, because what will, wait a minute. So,
even there, actually, the construction is you should that skipping should not have happened at every rth guy. It should happen at every r plus first guy because there must be a linear constraint among r plus 1 guys, not r guys. So m0 plus m1x plus you'll go all the way up to mr xr.
no, it is.
To the R.
See, the thing is, you understood, right?
Start from x to the R.
No, that is
Then
fine.
you
but
must take
then
every
I
R
think
plus
here
one.
it's sufficient for you to just have. I mean, in fact, I think this is impossible to satisfy. But if it was alpha 1 to the r plus 1 must be equal to alpha 2 to the r plus 1, etc. Then we know how to satisfy.
Okay, I
Yeah.
Okay, you're right.
That's the only restriction.
Yeah.
And for the
Got it.
polynomial also,
Yeah.
you have to start with x to the power r,
Uh-huh.
but then you have to skip every r plus first power. Right?
You have to come every r plus first power.
Why is that?
Because you want in each block you want r plus 1 guys, right? R plus 1. So the first block.
No,
is
but
R-
that's exactly what.
No,
R,
so this is-
r non-zeros, the r plus first guy is non-zero. Then r non-zeros, r plus first. That's exactly what you written there.
Right. So you are right. This has to be R plus 1, but
Yes.
I think it's correct. Okay. Because then in that case, so that's what I was thinking. Which is the one we can pick and show that. So basically, what will happen is that when you are evaluating f of x, which was m0 plus m1x plus plus m r minus 1 x to the r minus 1 plus m r x to the r plus 1 and so on, right? So if x to the r plus 1 was constant, so this one will fall back to the zeroth term. The next one will fall back to the first degree and so on, right? So in that partition, effectively, if you look at, right, only within that partition. So it is like saying that I have a polynomial, SH polynomial, but I am looking at what is the effective polynomial only within that repair group. Okay, and that will have a degree only up to r minus 1.
Not R, which
is not r.
Yeah.
Okay, so generally it will be r, but we are reducing it by 1, and that is that reduction in 1 is helping you in the repair. Okay, why is that? Because if I have a degree r minus 1 polynomial, then r points are enough to calculate that polynomial. Correct? So if r points are enough and 1 point is lost, once I have that polynomial, I'll be able to interpolate as the lost point also. Correct?
Yeah.
Okay. So yeah, thanks for this text. I think I would have spent a long time trying to figure out. Yeah. Okay. So this is the essence of Tamabara construction. They have many of these things can be slightly, in the sense that these polynomials, they will again make it big class of polynomials instead of just x to the r being constant and so on. So there are other ways to do it also, but this is the core essence of the Tamabara construction. The idea is just this. Okay, and yeah, so because it's such a neat construction, I like it because of its nice polynomial properties and so on. Okay, locality also we have seen how it satisfies minimum distance. Also we have seen the minimum distance only comes from, like when you are skipping these powers, what is the maximum degree? I mean, in the sense, sorry, what is the degree of the polynomial that you get? Okay, and that will determine the minimum distance, because if you have a polynomial of certain degree, you will require one more than that number of points. Right, and that will be, you can equate it to d min minus 1. Okay, so this is the thing about locally repairable codes completely. I mean, I think if you want everything in a nutshell, almost this is this. Okay. There can be extensions to, like, we have done extensions to multiple parities and so on. Okay, instant multiple erasures and so on, but all those things you can extend ideas from here easily. Any questions? Maybe I'll pause and then switch to next topic known as maximally recoverable codes.
So how does the field size look like as a function of k and n? I guess it can be omega, order n, etc. Basically you need some field in which there are r plus 1 groups of 2, r plus 1 groups of 3 or something like that. Whatever is that constant.
Just choose q to be such that q minus r plus 1 divides q minus 1. Therefore, you have an element of order r. So u will be the cyclic group that 1 omega, and all the posets of it will be the other bits.
Okay, that's enough. Okay.
Yeah, you just read it my entire lecture.
Oh, really?
I did 1 hour 45 minutes, a minute and a half.
Super. Okay. All right. So then I will do the next part, which is maximally recoverable, because I don't know how much time I have. But, for that I maximally recoverable codes. Can I give some basic details here? I'll just show you a particular thing. So let's say I have a systematic LRC with the following structure. So basically, I have, let's say, n equals. The examples are too hard to remember, but I think I'll come here the point. N equals 15, r equals 4. The number of is k equals 10. So I'll just call this M1, M2, M3. So, this is one structure of a systematic LRC where K equals 10. So I'll have 10 message symbols and the whole thing. Okay. Q1 is a local parity. So Q1, Q2, Q3 are local parities, and P1, P2 are global parities. So the way I have shown you previously, the local and the global parities were in the parity check matrix. Okay. Another way to think about it, local and global parities, is from the generator matrix itself. And this is like the generator matrix view. So what is meant by local parity here? Q1 is a function of a linear combination of M1 to M4. Q2 is a linear combination of M5 to M8. But P1 here is a linear combination of M1 to M10. Okay? And P2 is a linear combination of M1 to M10. Okay? So this is the structure that we have. Okay? So we are starting with, as you can see, we are already starting with disjoint repair groups. A linear code with disjoint repair groups. Linear. I mean, linear is understood. I mean, I am not, because I am not going to the other thing. Linear LRC with disjoint repair groups. Right? And still, it is not, I mean, it satisfies the locality is maybe kind of okay, right? Because as long as the coefficients are non-zero, it will satisfy. But whether it satisfies again minimum distance or not depends on what linear combination you are picking. Okay, so that part I'm still putting, I'm not, I'm assuming that we will design it properly. Okay. The coefficients I'm not telling you. All that I'm telling you is Q1 is a function of these four, Q2 is a function of these four, and so on. Okay, this is so this I will call as, if you want to call, I will call it as LRC topology. Okay. So which only tells you what symbols are functions of what, but doesn't tell you what are the actual coefficients. Okay. So the thing is, so suppose if I give you one particular erasure pattern. Okay, so and one thing, again, note that any d-min minus 1 erasures can be corrected, can be recovered. There is no pattern here, okay, in the sense that at least with respect to d-min minus 1, so that many can always be recovered. Okay, because again, because there is a fact, if you have d-min minus 1, if you remove d-min minus 1 of them, the rest are n minus d-min minus 1 plus 1 coordinates. Okay, and those can have at most again rank k. So basically, you will have all possible combinations. So every two, so what it just means is that if I remove, if I have a code word C1 to Cn, and I remove any d-min minus 1 of them, okay, still whatever is remaining are all distinct. Okay, this is a basic property of a code again. Okay, all these are equivalent properties of a code, which we'll use one of them whenever required, kind of. Okay, so the thing is, any d-min minus 1 erasures can be recovered. But now in the maximally recoverable codes, we are trying to go up to n minus k erasures, okay, and see what are all beyond d-min, what are all the erasures which the code can recover from. Okay, above n minus k is not possible, so that also is clear, because once you lose more than n minus k, you are anyway, your set has become of size k minus 1, which means that you definitely have lost information, right? So between d-min minus 1 to, between d-min to n minus k, number of erasures up to n minus k. So in this, for LRCs, you want to understand what are all the erasure patterns which can be recovered. Okay. Right?
And you're only considering erasures, no bit flips and stuff.
No bit flips and stuff. Actually, that's a nice question. Thank you for that. Because maybe we could define LRCs for that too. Thanks for that. Okay, so I will just show you what it is called as. It's called information theoretically recoverable. I don't agree to that terminology that much, but I don't know of a better terminology. They have used it. So what we will say is, what are information theoretically recoverable erasure patterns. So what I mean by this is, I will show you one pattern, actually two patterns, and I will argue that one is recoverable and one is not. Okay. So this is one pattern, one erasure pattern. Right? And the same thing for the same code. Q1, Q5, Q6. Q3. Q2. Okay. Right. What is the catch is that here this pattern, okay, is not information theoretically recoverable. Okay. In the sense, what it means is that you cannot assign any coefficients to these local parities and global parities, any coefficients. So all I say is, your code, whatever you design, should satisfy the structure, right? So which means that local parities and global parities, you are allowed to choose that. I'll tell you Q1 should be a function. Which coefficients you pick yourself, right? So that coefficients you have the freedom to pick, but that structure has to be satisfied. With that structure, this pattern cannot be recovered by any set of coefficients that you choose. Okay? So that is why this falls into the class of information theoretically not recoverable pattern. Okay, and that number is 5. Actually, it lies between these two, I think. Okay, for this code, I think it lies between those two for the optimal code, whatever. Okay, and the intuitive reason why this is true is that here, if you see, I have removed all messages only. Even there, I have removed messages only. So the parities are like linear equations which are helping you. Correct? So M9, M10 will not help. There are parities which are helping you. I mean, if there are M9, M10, they're just subtracted from the parities. That's okay, right? So, but then now here, if you see, I have 5 unknowns. It looks like as if I have 5 equations, okay? But this is dependent on these two. Okay, in the sense, this is dependent on all these. Actually, it is dependent on P1 and P2. Okay, after you subtract M9 and M10, right? So, which means that this is not helping you at all in this erasure pattern, which means that I have 5 unknowns, but I have only 4 equations, which means this is information theoretically non-recoverable, irrespective of what coefficients I choose. Okay, the same thing doesn't happen here. So that's all that I can say. As of now, I cannot give you a code which will solve this, but there exists a code which will solve this. Okay, so the whole set of erasure patterns which have numbers, means the number of erasures lying in this range, can be put into either information theoretically recoverable or information theoretically not recoverable. Okay, and it is easy to understand. It's not that it's too hard to understand. And there's a see, not recoverable is from that kind of arguments. Okay, something is not recoverable is from that kind of arguments. Okay, so something is information theoretically recoverable, you have to show code. Okay, but then showing a code is what we will do is we take a big step saying that I will construct one code which will correct all possible information theoretically recoverable patterns. Okay, and that is what is called as an MRC. And that's why it's called maximally recoverable, which means that, so MRC is something, the MRC is a code, okay, which satisfies a certain topology, whichever is given to you. Okay, so in this case, I'm giving you this topology, it's called LRC topology, right? But in general, if you want to talk about MRCs of different topologies, all that will change is what are the functions that you are allowing that will change, right? So MRC is a code which satisfies the topology, right? And recovers from all possible information theoretically recoverable erasure patterns. Okay. So one quick argument, so just for your intuition, that why does an MRC always exist, right? First of all, we have, for any topology, the first job it looks like is to kind of break this set and try to understand what are information theoretically recoverable patterns and what are not. That is one thing. Okay. The claim is slightly higher. The claim is saying that you have any topology, okay, and whatever is that set, there exists an MRC for that topology. Okay. This is slightly means even without knowing what are the erasure patterns, how are we claiming this? Okay. The claim itself comes from, suppose if you want to say, this erasure recovery itself, right, can be posed in terms of linear equation solving, as I have told you, okay, in terms of parity check matrices. Okay. So suppose if I say H times C is equal to 0, right? Whatever I have erased, I think this is from your talk. Okay. So whatever I have erased, so let's say I'll call this as erasure pattern is E. Okay. Whatever I have erased, I'll leave on this side. And whatever is non-erased, which is N, let's say, C is C and CN with interchanges, whatever it is, right? Right? So H times C is equal to 0, so H times C will be equal to H times minus Cn. These are all the things that you know, okay? So which means that this should be linearly independent, right? So this being linearly independent, with if you assume, so what is the brute force way to design these coefficients? One way to design it is saying that I will assign a variable for each coefficient, whatever it is, right? And this linear independence condition, I will transform into a determinant condition. Correct? So that determinant of some multivariate thing being non-zero is one condition you will get when you want to correct one erasure pattern, let's say, right? And I will have, by taking so many erasure patterns, I will have multiple multivariate polynomials, all of which you want to be non-zero, right? So there is, say, these things called combinatorial null-Stellensatz and all that, if you have heard of them, right? You can always assign polynomials, these multivariate polynomials, values from a high enough field, as long as they are non-zero, okay? Right? As long as they are, that polynomial itself is non-zero, you can always go to a high enough field and you will have values which will make that polynomial non-zero. Right? You can make an assignment such that the polynomial is non-zero. Okay? So what again that means is that if you take the determinant for the information theoretically non-recoverable pattern, that becomes 0. Okay. So that is the only way that it is not solvable. Okay. Otherwise, in variables, if it gives a non-zero polynomial, it is a recoverable pattern. Right? So that using that connection, that you can put the populate the H matrix with variables. Okay, and that each information theoretically recoverable pattern which will give you some non-zero assignment, because there is a, it just means there is a code which will actually solve it, no? Which means it's a non-zero assignment. And that solves the problem that MRC with combinatorial null-Stellensatz solves the problem that MRC always exists.
But there are exponentially many patterns, right?
Yeah.
And so you have to make it fit size large.
Very, very large. Yeah. Okay. So the field size, bringing it down is the main thing in MRCs. What is, and also, so there are two ways. One is that even MDS type conjectures are not known. I mean, there are lower bounds on field size which are known, again, which may be loose. It's that, see, MDS conjecture says there's a lower bound on field size of an MDS code, right? Similarly, there are things like there are lower bounds on the field sizes of MRCs themselves, which are not linear in n. Okay, there'll be some n power h or something like that. There is some other parameter, it's polynomial in n. Okay, so such bounds are there, and also there are constructions that there's again a gap, enough gap between the two.
So we are just stating that there are topologies for which an MRC will require very large field sizes.
Yeah, I mean even this topology will require field sizes large.
No, exponentially large field sizes.
Exponentially, so that question is not answered that way. So mostly MRCs are studied for topologies of interest which are like simple enough.
No, so are they simple? So I want to ask two questions, both positive. The negative question is, are they simple topologies for which any MRC requires very large field? And the other is, are there simple topologies for which you have MRCs with polynomial size fields? These are the. Do we have?
No. So the second part I can answer. There are simple topologies for which it will require polynomial size. And I think the constructions are also polynomial, but the polynomials don't match or something. So that is there. Okay. But are there topologies for which results are proved that it requires exponential? Maybe, I think some product kind of topologies may have been suggested, but it's not explored fully, I would say. Okay. In a sense, other than this LRC and the product topology, not many topologies are studied as such. Okay. So yeah. Okay. So yeah, so how are we doing in terms of time? I can present one construction of MRC if that makes sense, but otherwise, yeah. Because I think one construction of MRC that will kind of, I wanted to just cover two things. One, which so there are these codes called Gabrielian codes or maximum random distance codes, which are analogs of Reed-Solomon codes. So that way it is easy for me to present directly. Okay. So that thing gives an MRC. So that's what I can tell. I will not perhaps connect as to why it gives an MRC. Okay. And I'll also give another parity matrix thing, which it gives a certain better field sizes and gives MRC construction. Again, but I will do it quite quickly just to tell you what are new there, but skip all the proofs kind of. There's an MRC construction there. Okay. So I'm back. Is it that I'm back? Okay, then now I can erase, I think, no problem. This is all very elementary stuff. Yeah, so I'll not take anything more than 10 minutes perhaps. Hopefully. Okay. So MRCs are constructed in two ways. One is used through generator matrices, and through generator matrices means what I am going to tell you directly is a generator matrix. Of course, there will be parities matrix for that, but the description involves only generator matrix or parities matrix. So for that, again there are message polynomials M02 mk minus 1. But now what we do through the generator matrix thing is that, okay, by the way, one thing which also again one dot that you have to correct in your mind is that MRC, the whole description itself, I never told that it is an optimal LRC. Okay. But it's a small proof that you have to work out to say that an MRC is an optimal LRC. Means it meets the singleton bound with equality. That is easy to see because of course it will recover everything below d min minus 1, so the minimum distance also will be satisfied. Okay. So now M0 to mk minus 1. This is coming from mk. And then we are forming now a message polynomial. Right? Fx, which is called the linearized polynomial. Okay, this is what the linearized polynomial is mi x to the q to the I. Okay. So I think I am skipping something here. This is actually an extension field. I think it is some f q to the m or something. Okay.
There are two fields. There's a base field f q,
Yes,
there's an f q to the
yes,
m.
yes,
And you are allowed to have q bar, right? The base field to the power.
yes, yes. Okay. So I equals k minus 1. Okay. So these are called linearized polynomials. The messages themselves are coming from f q to the m only. Okay. To the m. So mi's are themselves coming because that's the code is over f q to the m. So that's what it is. Okay. The polynomials are like this, and we are going to have an MDS code by evaluating these polynomials. Then I pick alpha 1, alpha 2 up to alpha n. So if I want it to be MDS also, and actually it will satisfy more properties than MDS because you see that we are going to much higher degrees than what a Reed-Solomon code requires, right? Here earlier we were going up to degrees of k minus 1, here we are going up to q to the k minus 1, right? Still, as of now, we are asking only for the MDS property, but these class of codes, whatever I'm going to describe, are called maximum rank distance codes. So they have much more structure than general MDS codes or Reed-Solomon codes also. Okay, is alpha 1 to alpha n, which have to be picked, are all elements of, so they belong to fq power n power m. Okay, so they are vectored in this, and this alpha 1 to alpha n are linearly independent over fq. So that is the choice of points that we do. Okay, right? So if you see in the previous structure, whatever I have, right, n1, n2, dot dot dot. I hope you remember the numbers. N was equal to 15, and k was equal to 10, and so on. Right? So here we are picking a k equals 10 points, right, and making an MDS code of it, which is of 12 points, which was giving the 2 global parities extra. Okay, so that is the first step in this construction. The first step is, take a message polynomial, right, and evaluate them at 12 linearly independent points in the field. So that already gives you m has to be equal to greater than or equal to 12, because m is less than 12 means you will not have that many linearly independent points also. Okay, so m has to be greater than or equal to 12. Okay. So you take this message polynomial, evaluate them at 12 points. If that is the case, and so let's say you do it in, so as of now I'm not describing the systematic form, so not much. So then what I have is, I have f of alpha 1, f of alpha 12. So I had initially m0 to m9. This I am getting one intermediate step, which is a 12, 10 MDS, but there are also MRCs. But that doesn't give me my n equal to 15 yet, right? So what we do is that in this, we take 4 points each. So f of alpha 1 up to f of alpha 4. Okay. Then f of alpha 5 up to f of alpha 8, and so on, right? So for this, you just add one parity, okay, which is the sum of f of alpha I equals 1 to 4. Okay. So that will give you your fifth point. Okay. Do that for the next set, and do that for the next set. I'll give you a code of length 15. Okay, it will have, locality equals 4, so that also will be satisfied. Dimension is 10, right? And what else is required, by the way? Yeah, that it has 2 global parities and all that. If you write the parity matrix of this, you will get that 2 global parities and so on. So all those things you will get. Okay, that this is an MRC can be proved. Okay, so similar trick you cannot do. So the natural question to ask is, we could have done this with Reed-Solomon codes also. Okay, the Reed-Solomon codes, whatever you get, you cannot prove it's an MRC. Here, this can be proved that it is an MRC.
What's the topology under which an MRC? What's the same?
The same topology which we saw before. That one.
Oh, okay.
Yeah. Right? So, and as you can see, because I've started with the message and I've told you what all steps to do with it. So you can write the generator matrix quite easily for this. So I call this a generator matrix approach. Okay. And similarly, there is, but again, so as you have seen, the field size required is to do the well. It depends on
this construction is very much tied to that particular topology. This is a kind of universal set of construction. Let's say I give you n and k, but I can choose whatever topology I want consistent with that n and k, and have a code that satisfies the same reciprocity.
No, that is not possible. So because in general also, right? See, because if you are saying
bound doesn't depend on that particular topology, right?
It depends. Which bound?
This singleton bound.
A singleton bound depends on the topology. So if the topology changes, the bound changes. So because
this NKR, right? It depends only on this.
So see, but it depends on that it has locality R, and that is a slight weakening of the topology that we have.
Right.
See, we have slightly strengthened it by saying we want disjoint parities. Right. But even with the previous thing, whether you can say so the thing is in the topology, I think the one thing to specify, otherwise it is not clear, is what you are saying is, can we just say, my topology is like just locality R, right? In that case, there is no unique way of saying that this will be a function of these, because there can be multiple codes, okay, such that locality R's definition is satisfied. Okay. To simplify things, people have done this. Okay. But can we go back to the previous thing? Yeah, it is not clear to me. Means in the sense what to do with that. Okay.
Right. So in that case, design a code and just publish it, and anybody consistent with that parameters, they can use this code for any topology they want, right?
So any topology still is not clear. Consistent with the locality, you mean? Right. Yeah, that is not studied according to as far as I understand. See, one thing is that there are some structural results which say that suppose if one of these n divides or some divisibility is satisfied, then it is necessary that the code should have disjoint repair groups. Some such structural result is there. Okay.
I see.
That actually we have proved, or some, even in Gopalan's paper, they have an earlier version of the result. Some structural result is there. Maybe that is the motivation why they have said, okay, without loss of generality, we will take disjoint repair groups. Right? Yeah. Okay. So again, I'll end quickly now. So the parity check thing, which gives better field sizes than this q power 12. The only difference is it's like this. I mean, the way I want to think about it is like this. Okay. So when you have an MDS code, right? So let's say you have an n, n-3 MDS code, right? You could design this in the generator matrix also, or you could design this in the parity check matrix also. And it is always beneficial if you design where the number of entries are less somehow. Okay. So suppose if you want to design an n-3 code, if you do the Reed-Solomon and do it in the generator matrix way, you will get a much higher field size than if you go to the parity check matrix way. Okay. So then that is because the other side of this is just an n-3 code. Okay. And that is precisely the advantage that you get when you go from generator matrix to parity check matrix, even in this construction of MRCs. The way it is done is that the local parities are whatever they are. So all these local parities are, either let's say I can kind of put all ones, for example, not an issue, right? Okay. And taking values from the base field, right? But then here there are rows which are q powers of distinct elements. Okay. So I'll have alpha 1 power q, alpha 2 power q. I mean, first is alpha 1, then it is alpha 1 power q. By the way, am I doing it correct? I think so. Yeah. Alpha n, and then I have alpha 1 by q, alpha n power q. Okay. So this, as you can see, you cannot say as if there is some polynomial I'm evaluating. Okay. It is satisfying some linearized, the code word is satisfying some linearized polynomial kind of equation. So that's what that you can say when you look at the global parities, right? And if you design this way, for whatever some sets of parameters which are for which it has advantages, you get field size better than generator matrix. Okay, but here again, if you pick all of them to be linearly independent, that also is fine, but it is not necessary. So there is some notion called T-wise independence. Okay, right? So if I pick these alpha i's, or in particular actually differences of these alpha i's in some way, because so there is a whole lot of thing to it, but if they are picked some T-wise independent, okay, then you can guarantee MRC with this structure. Okay, and that actually is, once we redefine the conditions required for MRCs with respect to this linear independence, it is clear what's going on. It's not too hard to follow, but it will take another class, for example. Okay, whatever. Yes, right? So using this T-wise independence, it's not necessary that all N are independent. Some T which is less than N-wise independence is enough. Okay, to make this an MRC.
So T-wise independence, you're saying you choose the points alpha 1 to alpha n, which are T-wise independent.
So the T-wise independence just means that I have this alpha 1 to alpha n, let's say all distinct, but I pick any T of them, they have to be independent. It's not necessary T plus 1, T plus 2 be independent, not necessary, right?
So in some sense, so this is stating that if you view the code word as a polynomial, the alpha is the root of that.
Yes.
Rather, alpha 1 is the root of that polynomial, because it's a root of the linearized polynomial which the code word is representing.
No, not really, because here actually there are rows. See, this is the one which will multiply the code word. So it is not alpha 1 is not.
Okay, fair
right?
enough.
It's not even getting that.
The code word is not sitting in the
Correct.
Okay, fair
So
enough.
that's why it's like, see, it looks as if it has close connection to that, but somehow.
Okay, fair enough.
Yeah. Okay, so thing is, but again, finally, the property which will be useful in proving that this is an MRC is like, see, in the Van der Waals matrix, what we said was there was this K cross K, Van der Waals matrix, any K cross K are linearly independent. So that is what we have. Similarly, for the Q analog also, right? So I will write it as alpha power Q power 0, alpha 1 to the dot, alpha n to the 0. 1 q to the 1 up to alpha 1 q to the k minus 1. Okay. So this is the generator matrix if you take the linearized polynomial. This to the k minus 1. And in this also, any k columns are linearly independent if those are, the alpha 1 to alpha k of them are linearly independent. Okay, over fq. Right? So using that property directly in this matrix, kind of we can show it's an MRC. We don't have a polynomial interpretation, but this property will be used in this after some row reductions and all that to show that it's an MRC. So, yeah, so again, I have not come to my work at all. So we kind of extended it to other topology called hierarchical locality, okay, where there are two levels of locality. Okay, so that is one part. And we have some work in product topologies also. So product topologies is like very, very not at all understood. Even now, like there have been like maybe 3 years, 4 years since the first paper has come, but still it is like a quite tough problem. So the product topology just says that you arrange all your code word as if it were a matrix. Okay, so some m by n matrix, right? So each row is a code word, right, of a particular code, each row, and each column is a code word of a particular code, right? So that kind of topology is even the erasure patterns which can be corrected, okay, or the field size is needed, or the constructions, anything is not known at all. Some progress is made.
Columns, the rows are code words. I mean, they should be locality divided.
Sorry?
They should be locality divided, both the columns and the rows.
So every row is a code word of a certain code, and every column is a code word of another code. So there is this n by n matrix, right?
Oh, okay.
So it will be like, it is actually satisfying more than locality if you see, because it was enough if only rows were code words for locality to be satisfied. Okay. The fact that we are asking even the columns to have the thing. It is like as if this one is covered by two parities which are local in some sense, right? Okay.
I think these are often called tensor codes.
Tensor codes, yeah. Tensor codes. Yeah. So for that topology, I mean, though some progress is being made, I mean, we have done something, and I think Shivakrishna Gopi is from Maximally Research. They also have work. It is heading, but bigger problems are still open in this topologies. And of course, other than these two, no other topologies explored, so there are a lot more topologies to explore.
So let's thank Lalitha for the wonderful talk. If you have any questions, you can just catch up with Lalitha during the lunch. All right.
Thank you.
Thank you.
Thanks a lot.